In this video, I want to talk about two things. One is to determine whether a function is a one-to-one function. The other is whether two functions are inverses of each other. Let's look at this h of x defined as a collection of ordered pairs. I do have a picture here for my h. So 4 get mapped to -5, 6 get mapped to 1, 2 to 4, 0 to -3. First of all, this relation does represent a function because we don't have x value goes to more than one different y values, so it is a function. So not only this function, it also a very special function, which is a one-to-one function because we don't have different x values goes to the same y. So in this case, each of the x values get mapped to a distinct y value. So it is a one-to-one function. There are other ways we can check whether a function is one-to-one. For this, we're based on definition. So if you have the graph the function, you can determine whether the function is one-to-one by using the horizontal test. So we're not going to do an example for that one. Rather, we will do an example for a function which is defined by a formula. Say for this function here. So we have function f of x defined as the absolute value x minus 3, and we want to determine whether the function defined in such a way is a one-to-one function or not. So one-to-one function, by definition, means different x values has to be mapped to different y values. Okay. So to check this analytically using the definition, we're going to set the input x being two different values. It can be any two different values. Say, let's call them a or b. Okay, it can be either a or b. We're talking about two different x values as input for this function f. And then we're going to evaluate this function at these two different inputs. When input is a, we have f of a equals the absolute value a minus 3. When x equals b, f of b equals to f value b minus 3. So if f of a equals f of b, then we're going to have correspondingly this equation. And this is going to imply absolute value a equals absolute value b. If two numbers have the absolute value being the same, either these two numbers are the same, or these numbers are opposite in sign. So this says we can have two different input that potentially give us exactly the same output. So that's why this function is not one-to-one. So basically, if you want to check this analytically, and you start with the function value for two presumably different inputs, and then this has to imply those two inputs being exactly the same. If that's not the case, then the function is not going to be one-to-one. So if functions are one-to-one, then the function is going to have inverse. What do we mean by inverse? Inverse of the function means the effect is going to undo the effect of the original function. In other words, if you have two functions being inverse of each other, then their effects will be canceling. So what I mean is that, say you start from an input being x, and we'll map through a function called m, and then further map through a function called n. And eventually, the effect from m and n is going to be canceling out. That will take you back to the original input x. And the direction you do this doesn't matter. So now you start with input x, and you first map through the function n, and further map through function m. Eventually, that should give you where you started as well. If that's the case, then we're going to say m and n are inverses of each other. So let me explain this through a concrete example. So we're going to check whether these two functions, such defined, are inverses of each other. So by definition, we're going to check the composition of these two functions in different orders. Let's start with m circle n of x. In other words, is m of n of x. So the input x first mapped through function n and then mapped through function m. This gives us m of n. N is 2x plus 5 over x. And then we evaluate the function m at input being n by substituting x with the formula for n. This gives us this form. So this is the formula for the composite function defined in such a way. If you simplify it, so 2x over x is 2. 2 minus 2 is 0. So the bottom is just 5 over x. And then you flip it. We're dividing it. It just flip this quotient. That gives you x over 5. 5 got cancelled. Eventually you get x. So we start from x and we get back to x. This says m and n undo each other. So we're going to check the other direction as well. This time, we're going to start with function m and then further map through function n. In other words, we're doing n circle m. That's going to be n of m, which is defined by 5 over x minus 2. So we can evaluate, where we can write the formula for this composite function by substituting x in n with the formula for m. So before I do that, I see a way to simplify the formula for n. That's going to make my calculation a little bit easier. So I'm going to start with simplifying the formula for n. So n of x equals 2x plus 5 over x. I divide x into each of the terms in the numerator. That gives me 2 plus 5 over x. Now I'm going to substitute the formula for m into x. That's going to give me n of 5 over x minus 2 equals 2 plus 5 of this whole thing. Again, divide by this, you just flip it and multiply to f5. And 5 got cancelled. Eventually you get x minus 2 from the second term. And then you have 2 in front of it. Adding up to this, you got x again. So basically, this is suggesting you start from x, you first mapped x through m and further through n. Eventually, you get back to x again. This is again suggesting the effect from m and n are canceling from each other. No matter which order you do it, you start from n, then do m, or start from m, then do n. Eventually, the effects all going to be cancelled out from these two functions. So by definition, we're going to conclude these two functions, m and n, are inverses of each other. So basically, to check whether two functions are inverses, you're going to check these two composite functions. And you do it in different order. Eventually, if all get back to x, then we can conclude by definition these two functions are inverses.